manifold, I just want to have a bit of a thing that the mission has been accomplished. So everyone knows, at least the ones alive now, is there anyone who's still struggling with the notion, what does a smooth manifold is? No, so this is good. Mission accomplished then, George.
Great job.
Thank you for George and Bob for the study sessions. By the way, Bob, I saw the message on Discord. There was a typo, so this could actually be one of the exercises as the crash course comes to an end, to revisit the slides to see any typos, and then send them back to me. I will try to correct them and update the slides. So thank you for that. Okay, so let's dive into part A. So part A is essentially, we have seen what smooth maps are from Rn to Rn. So, we have seen that the transition maps, which are, maps from parts of Rn to parts of Rn, are smooth. So the idea is, can we use them? Can we actually extend the notion of smoothness at a manifold level? And the answer is yes. This is exactly what we are going to do with this definition. So given two smooth manifolds, X and Y, where X is n-dimensional, Y, let's say, is k-dimensional, with the respective atlases. So I've labeled the atlases AX to be the atlas of this first manifold, and AY, the atlas of the second manifold. So a map F from X to Y is smooth at the point P if there are two smooth charts, at least two smooth charts, that we labeled UX phi1 and UY phi2, satisfying these conditions. Maybe I could have bunched them all together, but I decided to split them in three conditions to make it much more clear for most of you. So the first condition is, sorry, the slide have jumped. So the first condition is that the point P has to be in the chart domain UX. Okay. In other words, the first chart is a smooth chart around point P. The second condition is that the image of UX has to lie in the chart, in the second chart domain, in UI. Or another way to say that is that F of P lies in the chart. The image of P lies in the chart UI. Okay, and then most importantly, this composition here, this composition is a smooth map. Okay, at a point F of P. Calculus 101, that what a map being differentiable at a point is. So it's in that sense. Here's a diagrammatic overview of the thing, general. I will give you another slide with more complete picture to give you a little bit of intuition of what this composition is all about. Okay, so you see the UX, the chart domain UX, and you have F, right? It goes here, and then you have this composition. Obviously, this composition is, as you can see from the diagram, is from Rn to Rk. Okay, so it makes sense to ask about differentiability. And here's a more complete diagram that I hope I didn't make any typos, that hopefully give you a little bit of a better visual picture. Apologies for my for my artistic thing. So if you notice any typo, please ping me on the thing. But hopefully this gives you a little bit of a picture. And then, so that's a map being smooth at a point. So to generalize it, we say that the map is smooth if it is smooth at all points in the manifold X. Okay, so if it satisfies the conditions that we have just seen before, it means that we say it's smooth. Okay, so in a nutshell, this composition, as you can see, essentially enables us to define the notion of differentiability at a manifold level. So that's the good takeaway. And also, in a nutshell, it makes us, enables us to make a smooth coordinate change from one manifold to the other, right? So we can, we are in just like the diagram is showcasing here, right? We are here. We then we have the possibility to go and change to use a coordinate representation of that point in this thing, in this using this on this manifold. Now, this composition is called, obviously, the coordinate representation of F, as most of you might already guess. And another thing, obviously, is that this map can be from F can be from X to itself, right? In fact, this is what we will see when we some of the extension of this when we talk about diffeomorphisms and these things later. So now here's a challenge. The first challenge, yeah. That's why I told you we are not going to cover too much, but I have quite a few challenges. This is the easiest. This challenge one is very easy. The second challenge is a little bit more harder, but yeah. So just before, by convention, we will write C infinite of X to denote the set of all smooth maps, real valued smooth maps that go from the manifold, smooth manifold X to the reals. Okay. So here's a challenge here. I know it's like the thing. I'm being a little bit cheeky, but practice. This is what I would like you to do, so you feel comfortable with this. For those of you who've already, feel a little bit comfortable, obviously you don't have to go through all these things. But I really encourage you to go through this in these things, construction, especially on this construction stuff, for you in order to for these things to stay in your head, for you to gain some practice. And the second challenge, this is a little bit harder. So in here we have like so we have an n-dimensional smooth manifold, and we define the notion of pointwise scalar multiplication as this. So alpha times, I'm using times here, times F equals alpha times F of P. So this times here, this product is anything on the reals. Huh? Okay. So the same here, we can define the pointwise addition. F. I'm using this symbol here, because it's just a symbol. Don't confuse it with other stuff like we went through, like direct zooms and these things. View it just as a symbol, a formal symbol that I just, I could have used another symbol, but I decided to use this. So F1 plus F2 at P is defined like this: F1 of P plus F2 of P. So this addition also happens in R. Just to be clear. So this addition happens in R because this is real valued function, so it goes to this thing here. It goes from, obviously, from the manifold to R. So this addition here is to be understood on a thing to be on R. Okay, so the question is, with the pointwise addition defined above, whether this is a real vector space. Module 1, you know what a vector space over a field is. So I'm pretty sure a lot of you already know the answer to this. For those of you who don't feel comfortable, especially those who are more new to this, not coming from maybe physics or advanced background in physics or mathematics, it's a little bit harder to think. It gets a little bit it takes a little bit of time to get used to this idea of functions, adding functions and these things, This is something that you need to start getting familiar with, because in functional analysis, it's all about these things, this type of stuff, this type of abstractions that we need. But just try to think about it, on the thing. It's the formal operations are defined like this, So the question is whether this forms a vector space. If yes, the question is, what is the dimension of the vector space, right? Because vector space has a dimension. So I hope you got. And then This is not for everyone, but for the super curious. Well, let's define a product. Why not? We define addition. Why not define product too? So another note is that don't mistake this with the tensor product. Again, I just use this just to, just a notation. It's just a notation. It means this. So view it in this context. So F1 times F2 at P is equals to F1 of P times F2 of P. So this product here also happens in R. Okay, so is just to be clear. Now the question is, if this multiplication together with the addition here makes this C infinite of X into a ring with identity. Okay. So, and the question is then, what is the ring identity, if that's the case? And also, what is the characteristic of this ring, right? Remember, in the foundation module, you can actually go back there to review the notions of ring and this type of stuff. And I guess this is also like the thing, whether it's a billion or no a billion, meaning, or alternate, another name is whether commutative or non-commutative ring. So I really encourage you to try to get this, because this is very important. This will lead us to the notion of algebras that we will not touch here. We will touch in the next level. So you're already halfway through to know what an algebra is, and this guy here is one of the important things that examples of an algebra, and you can equip it with more, like other structures, like a Poisson algebra, for instance, this type of stuff with a Poisson bracket. These things that we will touch in the next module. Okay. Do I have any questions somewhere? I just saw something pop. Maybe it's the.
I don't see anything. There was a comment